In our next example, we want to determine if the sum from n equals 0 to infinity of negative 1 to the n, e to the negative n squared, converges absolutely, conditionally, or diverges. So let's begin by considering the absolute value. So the sum from n equals 0 to infinity of the absolute value of negative 1 to the n times e to the negative n squared. This equals the sum from n equals 0 to infinity of 1 over e to the n squared. Now, this series is not geometric, nor is it a p-series. So our next possibility for looking to determine convergence is to look for a comparison. Notice, for integers, n greater than or equal to 0, n is less than or equal to n squared. So, e to the n will be less than or equal to e to the n squared. Further, we know that 0 is less than e to the n, which means that 1 over e to the n squared is smaller than 1 over e to the n. When you make your denominator smaller, the fraction as a whole with the same numerator becomes larger. So, and this is positive also. By the direct comparison test, since the sum from n equals 0 to infinity of 1 over e to the n, or more explicitly, the sum from n equals 0 to infinity of 1 over e raised to the n converges. After all, this is geometric, with r equal to 1 over e is less than 1. By the direct comparison test, we can conclude that the sum from n equals 0 to infinity of 1 over e to the n squared also converges. Now, that means that our series as a whole, the sum from n equals 0 to infinity of negative 1 to the n, e to the negative n squared, converges absolutely. So again, the idea here is what we ended up doing is taking the absolute value of our series, or of the terms of our series. And then we applied the direct comparison test to conclude that the series of the absolute value of a sub n converged. So we're able to conclude that the series a sub n converges absolutely.